Okay, now it's on. Okay, Bismillahirrahmanirrahim. Good morning, everyone, and welcome back to the SPEPAPG Annual Technical Conference 2021 live morning GNG session, which covers exploration, stratigraphy, and sedimentology. We are joined by Saeed Tariq Hassani from PPL and Mohammad Mujahid from MPCL as chair and co-chair respectively for this session. I would like to introduce two of them. Mr. Saeed Tariq Hasni has been working in the petroleum E&P sector for the last 33 years after obtaining Bachelor's of Science with honors and Masters of Science degrees, both in geology from University of Karachi, Pakistan. He has worked locally and internationally and stationed in several international locations. He has a wide variety of technical and management experience. He has authored several technical papers and presented them in presentations all over abroad and in local conferences. Presently, he is working for Pakistan Petroleum Limited as a senior manager exploration and heading subsurface technologies and support services, that is STSS department, which provide all sort of GNG, operational and technical services to ongoing PPL's operation. Coming towards the co-chair, that is Mr. Mohammad Mujahid, he is working as manager exploration at Mari Petroleum Company prior to MPCL. Mr. Mujahid has worked for Spud Energy, Gulf Petroleum, POL, Schlumberger, and CGG in various parts of the world. Mr. Mujahid is a seasoned professional with over 27 years of diverse working experience in oil and gas exploration and development. He holds a master's degree in geophysics from Quaid-e-Azam University, Islamabad. Thank you.
Good morning. Assalamu alaikum.
All right.
So we are going to start the second session today. That's about the GNG. And the first paper is going to present by Adam O'Neill. He's probably the presenter and the senior author.
So the presenter for today's session will be Abid Riaz. So please join us on stage.
Abid Riaz. So he's the presenter.
Yeah.
So this paper is it is about the applying geological processes for this one is
First one is right.
Improving depth imaging uncertainties, full waveform inversion case study. Abid Riaz is the presenter. Let me introduce Mr. Abid Riaz. Abid Riaz is Managing Director of EIF Geosolutions. EIF. Abid specializes in velocity model building and full waveform inversion. Prior to EIF, Abid has worked for Down Under Geosolutions, Schlumberger, Fugro, and CGG in their London offices as a depth imaging specialist. Abid has 16 years of industry experience and worked on data from various geological basins around the world. Abid has published papers in the Edge, EAGE, First Break on the kinematics and dynamics of STI. Abid has a master's degree in petroleum geosciences from the University of Manchester, UK. I request Mr. Abid to present their paper.
Thank you very much. Thank you. Good morning, everyone. Today I'll be presenting a case study where full waveform inversion has helped resolving the depthing uncertainties, and it has helped with the depth conversion. And I will also be presenting an example slides from high frequency FWI. My co-author in this paper are Adam O'Neill, Troy Thompson, Matt Lamont. Obviously, they're not here. I'm presenting on their behalf, and obviously I have participated in this paper. The first step, I think we have to understand our challenge here. The challenge is in the seismic industry, we generally, the near surface shallow water is always challenging, especially when you have heterogeneous overburden, carbonates in this case. Travel time tomographies, travel time based velocity analysis always struggle resolving near surface where we have serious heterogeneity. And in this case, the data went through a series of velocity model building, lots of iterations of travel time tomographies and near surface velocity analysis based on the travel time tomography algorithms. But what we can see here is on the right-hand side of this section, we're only 100 meters away from our appraisal well, and our depthing to our well marker is not matching, and that's a serious issue for a production field. The reservoir by itself is sand, but the near surface it has a lot of localized heterogeneous carbonate, shallow carbonates, and that is causing the issue. Because we haven't resolved the near surface, we can't really get to the resolving the target reservoir at 3,000 meter depth. So what do you do in this case? Obviously, prior to now, 10, 15 years ago, you would heavily rely on travel time tomography, velocity model building approaches. And I'm sure we've all come across these sort of issues, but we would struggle because you would use a geostatistical tool or kriging methodology to depth convert your seismic from time to depth. At the well location, yes, you can match a well marker to a seismic reflector, but what happens between a well location and away from the well location, this is where the challenge comes in. So we need a better tool, better physics, better mechanism to resolve this issue, and this is what has happened in this case. So we were lucky we resolved this case, in this case study, obviously, we have resolved the issue. So we've dropped down the depthing errors from 50 meter down to 15 meter. So I'm going to start with the results straight away. So I'll show you results before and after full waveform inversion. And then I'll have some validation slides. And then it will be followed by high frequency full waveform inversion. So here on my slide, as you can see, this is a starting model to full waveform inversion. So it needs to be generally, it needs to be a very smooth starting model. Even looking at seismic scale length, this velocity model, as you can see, velocities are increasing with depth. We have a general trend. There is general structural pattern captured in the velocity model. There's a match to the well velocities at the well location. So generally, this is an acceptable model from a seismic velocity model building approach. But it doesn't resolve our issue, especially the depthing and the heterogeneity at the reservoir level. And that's why we need to go and we need to search for new technology, new tools, find new physics to resolve this issue. So I'm going to show what happens when we run 12 hertz full waveform inversion after that. So I'm just going to toggle a couple of times. So our starting model and 12 hertz, 20 hertz full waveform inversion. And you can see with full waveform inversion, we've captured a lot of detail. We've picked up localized velocity anomalies. We've got a significant match to the well markers and the well location, well velocities. There's a structural pattern now more clearly visible on your velocity model, so you can even interpret your faults on your velocity sections. We've added a lot of shorter wavelength detail to our velocity model, and there's a lot of information here that you could use as an interpretation product, not just helping your imaging, but also use that information, the velocity attribute, as an interpretation product. So it's a validation confidence factor that you could use for your interpretation. So I'm just going to toggle a couple of times. Now we have seen what it does to velocities. Obviously, looking at the seismic now, so our section here shown, it goes from late tertiary to Triassic. So that almost a kilometer section we are looking at here, obviously squeezed. So from seismic point of view, you would always think, oh, it looks like a high frequency statics issue. In reality, it's not. The issue is caused by the carbonates in the near surface, and we haven't resolved them, as I explained before, because the physics limitations, the physics behind available technologies prior to full waveform inversion failed to resolve these kind of issues. We are seeing localized sags, we are seeing pull-ups, push-downs, on your sides. We had lots of well data, lots of appraisal wells drilled locally. There's a lot of well information, and we matched to the well our sides, but locally, but away from the well, between the wells. This is where the problem comes in, and that's what we need to resolve. And you can see on the right-hand side of this section, the depth errors. You can see a clear bias towards the depth errors from late tertiary to Triassic. We're getting into almost 50 to 80 meter depthing errors. And that's a serious issue when you go to production fields, appraisal, exploration, acceptable to some. I have seen case studies where it's not acceptable anymore in the industry. You want to get down to 5-10 meters now with the tools available now. So it is an issue. And now I'll show you. So the section here is Kirchhoff pre-stack depth migration image here. And this was using travel time tomography velocity model building. The velocity model I've shown in the beginning. It went through a series of tomography iteration. And now, if I toggle that image against the image that has been migrated with the full waveform inversion, you can see there's a clear signs of validation. So A, yes, it's helping the depthing. That's our key objective. That is one thing. Like I said, depthing we can resolve geostatistical tools, kriging. There's all sorts of things you can do at the well locations to resolve your depthing. But your seismic in your structural image should correspond to that. They should talk to each other. And what you should get also, not only the depthing resolution, is the imaging improvement. So that's the sags and the pull-up and push-downs, they should reduce. Plus, the kinematics and dynamics of your seismic should improve as well. So we should see improvement in coherency, continuity, reflectivity. So everything, velocity and reflection coefficient, they're directly proportional to each other. So we should get improvement in everything. The pictures should talk to each other. If you see any less, then it means the methodology is not valid and it doesn't work. So we have reduced undulation. We are seeing a better tie to the reservoir. The sands are better mapped. And on the right-hand side, we can see the mist ice significantly reduced from, we were talking 50 to 80 meters before full waveform inversion. And now we're looking at 5 to 15 meters. We're into 1 to 3 samples, seismic samples. So this is a huge improvement and obviously reduces your headache. I mean, it makes the production field life easy, definitely. So, big uplift, and it is purely down to the technology behind that. So another validation, we had interpreter going on picking horizon on your depth stretch seismic. On the left-hand side, it was migrated with the smooth starting model that we used as input to FWI. And on the right-hand side, we can see a horizon, the reservoir horizon picked on the seismic migrated with the full waveform inversion. I think our picture speaks 1,000 words. So you can see that there's a better closure at the reservoir and good structure closure. The fluid contact is better defined. It matched, obviously it was matching the well prognosis as well. So we've seen validation. If I go back from the first slide, the seismic velocity model resolution significantly improved. The validation on the seismic structure by itself improved, the depthing improved, and the structure closure is more prominent now. So the technology hence works. So we've seen results. Now we need to understand the technology. I'm sure you're all familiar with the full waveform inversion, but I will just quickly explain the full waveform inversion methodology. So for full waveform inversion, we don't need to go and run series of velocity model iteration. You can take your raw seismic, recorded source signature, and a starting velocity model, and then the rest is the physics. Obviously, the analyst work comes in. You have to analyze results. I will be showing in the next slides. So what happens is we have a starting model. We create synthetics using the source signature. Again, source signature is a very fundamental item for this. I'm sure we've all seen hundreds of full waveform inversion, marine examples, but land is very challenging. Land source signature, the phase is always issue, but we have capability of doing both land and marine. Hopefully next time I'll be able to show you a land full waveform inversion case study. So source signature plays a very important role in the full waveform inversion. So you have a starting model. You create synthetics from your starting model and source signature, and then you compare that with the raw recorded short seismic. So, raw seismic against your synthetics that you have created from your starting model and source signature, and the mismatch between the source signature, so the synthetics and the recorded seismic is backpropagated as a residual into your velocity model, and you get an updated velocity model, and that's what you see on the right-hand side. It needs to go through many iterations, and you go through lots of frequency bands. You always start at low frequency. That's fundamental to benefit from low frequencies to get a background model as good as we can, and obviously get the deeper information at depth. That's very important as well. So low frequencies, very important to FWI. Your source signature, very important. But obviously, it needs to be right people doing it, and you get good results. So in terms of validation, as I explained, we need to make sure that our synthetics are matching to, or less than half a cycle to the recorded seismic. So that's where we are seeing on our left-hand side, our first seismic gathers are blue, turquoise blue wiggles are synthetics, and the gray is recorded seismic. So in the general, there is a decent match. So obviously at this scale, you think it's a perfect match, but we need to make sure that it is within half cycle. In this case, the waveform inversion started at 4 Hertz. So again, that we need to have that kind of low frequencies and offsets recorded in the seismic data. And then as we progress gradually, we generally go 2 to 3 Hertz up every iterations. So we would go from 4 to 6, 7, and then 8, 10, 10, 12, and so on. So we just need to make sure that synthetic match to our seismic is always less than half cycle, and that means your methodology is working. Like always, the second image, I'm sure we've all done it and seen the seismic industry relies on the kinematics of your seismic. So your gather needs to be, the flatness of the gather should improve, the coherency and continuity of the events should improve. They all should talk to each other. And the third validation, if we have a true recorded information, which is our well, then your methodology should talk to your well as well. Your velocity model, the updated velocity model from your full waveform inversion or any other methodology should show improvement in resolution when you are comparing against the well data. And the bottom left, you can see geometrical patterns. Very important that in terms of 3D, the maps we have here, or if you have 2D data, the geometrical patterns are followed in your velocity update. So, and we need to make sure that the well data is nicely matched, as you can see on the last image here. So that was my first part of the talk. The second part, I'm just quickly, I'll show you a few examples of high frequency FWI. So it's very important, I think, from where I come from, industry has come a long way. 10, 15 years ago, we wouldn't have thought about running a high frequency 100 hertz FWI. And why it is important, again, the picture you can see on the left, it is based on methodology I have shown on in the previous slides, that generally you would run 12 to 15 hertz full waveform inversion for your imaging, for your general seismic depthing issues, for your imaging. That is enough, because you get anything higher than 12, 15 hertz, you get into Fresnel zones, and then Kirchhoff migration struggles with that. For RTM reverse time migration, you could go to any frequencies, and that's not an issue at all. But if you want to save cost, and plus you want to have another validation on top of your seismic, something else, velocity attribute as an interpretation product, then in that case you can run a very high frequency full waveform inversion like we have seen here, 100 hertz FWI, and you could use that as a structural product. As you can see, from 12 to 100 hertz, a lot of faulting is here. Your lithological indicators are here. You can see stratigraphic pinch outs, lots of information. So that not only makes interpretation easy, but obviously inversion, the next step, is also made easy. I have a couple more images here. Again, so what we are seeing here is we have a 50 hertz full waveform inversion, and that was used, that went into inversion. And you can see that you don't have to obviously upscale your velocity model to the well. You don't have to use geostatistical tools. You don't have to create the well information. For what happens away from the well, you get a very high detail, high resolution, high fidelity velocity model, and that is showing you a fantastic match to the well and a lot of information. Here you can see the blues are your carbonates, the yellows are your sands, and in the near surface where you go from purple to light white color, that is they are localized shells as well. So a lot of information you can get from your full waveform inversion. I think going back to what I said just before, now we are living in an era where we have access to high compute quality computers as well. I mean, I have access to world's largest computer, and you can run full waveform inversion at any high frequencies. I have run, tens of thousands of square kilometers overnight. So we are lucky that we have that sort of capacity and capabilities and the physics. So in this domain, we should utilize, we should benefit from it, and make most of it. And that was my objective, to basically show you a case study where depth conversion, depthing uncertainty was resolved, minimized to a large extent by this new physics, new tool, which is full waveform inversion. And also, if you want, you can have a very high frequency full waveform inversion as a byproduct. I mean, it's just the beginning of a new era from where I see you can have access to as many attributes in the future. Fracture analysis, like we were talking about earlier in the morning, at micro scale, you need high frequency information for that. You will have that. You get Q factors. You can have lots of information, and this is just acoustic FWI. So when you go to elastic domain, there is no limit. So my conclusion, obviously, like we've seen here, the full waveform inversion has helped resolve the depthing uncertainty, and it's a great quantitative interpretation byproduct. Thank you very much. Please, if you have any questions, then go for it.
So thank you very much.
Thanks, Abid. Thank you very much. I think we still have a time for questions, right?
Yes, we have time.
Yeah. Do we have any questions from the online guest, or I open the floor if you have any questions? Abid is here for response.
Okay. Assalamu alaikum. My name is Samad Hassan, and I'm a senior geoscientist from PEL. I would like to ask you that what's the minimum resolution of the beds which can be resolved using this technology, especially in an area where there is very limited well control?
Okay, so generally talking, there is a frequency relationship with the resolution. So let's say if I go to 50 hertz, you can resolve up to 40 meters spatially and 5 meters vertically. So if that helps, but there's a formula that works out. You can go to 1 meter with 100 hertz, but obviously there's cost factors and all that involved.
Because I would like to know about it, because as you know that in the area Badin, there are middle sand, there's a body of middle sand, and there are shale sequences inside the middle sand which distributes the middle sand, especially in the southern part. While the middle sand is very well defined in the northern part of the Badin area, in the southern part it's quite deep and it's not that well defined because there are very scarce wells over there and very limited discoveries over there. So I was just wondering that will this technology will be helpful for us, because we have seismic over there, 3D coverage, but we don't have enough well control over there.
Absolutely. I think, what this case study that I've just presented, it explains that away from the well. And probably there's one factor that I haven't explained in my talk is full waveform inversion mean you're using the whole wavelet. So it means diffractions, it means refractions, it means reflection energy, it means multiples, everything. So anything that is there, the information it will derive from your whole recorded data. So it's not just relying on kinematic reflection tomography or near surface first arrival tomography. So it's meant to give you more details and accurate as well, because it is using more information.
Thank you.
Right. So one last question from the online. So Mr. Mumtaz Mohammed Shah, we have enabled your mic. Right. So can you type in your question and we can read it for you? Okay.
In the meantime, is there any question from the audience here? Okay.
Right. So Mr. Abdul Nasser, if you can unmute your mic and you can ask a question, otherwise we'll move to the next presentation.
Thank you, Mr. Abid.
Okay.
Yeah.
Thank you very much.
There's no more questions. Thank you very much for your presentation.
Yes. So we'll move. Yeah. Thank you, Abid, with a wonderful presentation. So we move to the next presentation.
Yes, we're moving to the next presentation, which is about the Cretaceous Paleogene boundary in Pakistan stratigraphy by Nusrat Kamal Siddiqui.
Yes, the Cretaceous Paleogene boundary in Pakistan stratigraphy by Nusrat Kamal Siddiqui. So what a presenter. Nusrat Saab is like an institution, and I think there is no need to introduce himself, but to refresh the minds of the guys who are with us online. I think there are a lot of them there. Nusrat Saab has over 40 years of diversified experience in geology, engineering geology, and petroleum geology. While he did his BSc honors and MSc degree in 1969, where I think most of us didn't born yet. So unbelievable achievements he did. It's about 25 years in PPL, started in 1981 and retired as a senior manager exploration from PPL. He published enormous papers on different forums. His book was, which he published, there was two books actually he publishes. One was Petroleum Geology, based on architecture and stratigraphy of Pakistan in 2016. Here, mic is on, yeah, 2016. And the second book was, basically he wrote on the life of Prophet Muhammad, peace be upon him. So today is a technical session, so we will present technically. We hope on the later stage, some down the road, he will present the life of Prophet Muhammad, peace be upon him, to the forum, maybe on the next meetings. So, sir, if you're listening, the floor is yours.
Thank you. We are thankful to the management of the ATC to provide us the opportunity to share our thoughts. Please note that my knowledge about the microfossils is rudimentary, but I have been to all the places being discussed in this paper with a keen eye about the physical appearance of the KPG boundary and the stratigraphic ages therein. And now, ladies and gentlemen, with the permission of the chair and with the thanks to my mentor and the co-author, Dr. Aftab Ahmad Bhatt, who made me the main author, the presentation will follow. It may be noted that a new approach and some new terms are being used, which may be different than the conventional understanding of this infamous geological enigma. Please bear with me, and I'm available to answer your queries or to justify our point of view. However, any query about the microspecies and their ages will be forwarded to Dr. Aftab Bhatt, and his response would be shared later. But before that, I request the chairman of the session that if any question is there, it may be posted through chat for me to understand fully and respond verbally. Verbal discussion can't continue. Sorry.
Noted, sir.
As per the definition, the stratigraphic contact between the Maastrichtian and the Danian rocks represents the Cretaceous Paleogene boundary. The radioactive layer associated with the KPG boundary in many places is most probably absent in Pakistan. Here, it is just a surface with iron incrustations. The N-Mesozoic global regression impacted the Indus Basin with different intensities. It was prolonged in the present day Kohat Potwar Hazara area, which is number 1 and 2 on the map, minor to moderate in Sui mainline Sui province, in Salman province, which is number 3 on the map, prolonged to absent in Kirthar province, which is number 4, and again prolonged in Badin region, which is 4 again. These observations are based mainly on the erosional level seen in the outcrops and on the well data of the Badin region. In the last slide, I will explain it further through a table covering the Indus Basin. In our opinion, the KPG boundary is absent in the Potwar Kohat Hazara region. We consider that there are 3 types of KPG boundaries: apparently unbroken, where Danian and Maastrichtian rocks have a disconfirmable relationship with iron incrustations at the contact; broken, where the Danian is missing above the Maastrichtian and the contact remains disconfirmable; unbroken, where the positional continuity across the KPG boundary is seen due to a perpetual translation. Cross-Concrora shale is the example. It is a west-east sketchy section across Potwar. It was made by Mr. Nizamuddin, a veteran now. The Hangu formation of Danian age is well developed in the entire region. However, prior to the beginning of the Cenozoic translation, there were tectonic upheavals and the Maastrichtian rocks were eroded away. Initial transgression seems to be shallow and with subaerial exposure, as residual deposits and coal is found at the base of the Hangu formation. Resultantly, the hungoclastics with residual deposits at the base and coal overlie the older tilted strata across an angular unconformity. With this setup, the KPG boundary cannot be delineated in Potoir. This is a stratigraphic section based on the field measurements along Suleiman Range and the wells drilled in the Suleiman lobe. The pup sandstone of Maastrichtian age is the datum. Please see the top of the section from right to left for the names of the data points. In the northern Suleiman Range, Dungan of Upper Paleocene age overlies the pup sandstone up to the Mughal Court section and represents a broken KPG boundary. From Tangisar to Prakhinala section, Khadro and equivalent formation overlie the pup sandstone where an apparently unbroken KPG boundary can be delineated. Further south at Khalgari Nala, the Khadro is again absent. All the wells in Suleiman lobe drilled a large thickness of the Ranikot group, with Khadro of Danian age being its oldest formation. It may be noted the depositional basin of the Ranikot group was where the Suleiman lobe is now. Under the Suleiman lobe also, an apparently unbroken KPG boundary is inferred pending final confirmation. The double-headed red arrows show where apparently unbroken KPG boundary can be delineated. The quality of this slide is regretted. It was published in 2004 in my APG paper about SML. Wasn't necessary to revise since. These are field photographs and a Google Earth image of Chiltern Range around Quetta. The white outcrop of Murray Brewery limestone can be seen here. It can the white this arrow.
Sir, we cannot hear you. Can you repeat?
The white outcrop of Murray Brewery limestone can be traced along Chiltern Range from Murray Brewery Gorge to Gawani Nala. Here, Murray Brewery limestone is overlain by Dungan limestone of the Depreciation age. It represents a broken KPG boundary. It is a modified lithological and biostratigraphic log of Murray Brewery limestone at the gorge after Elman 1979. Elman established Upper Paleocene age for the Dungan limestone above the iron incrustations seen within the carbonate section. The iron incrustations mark the top of Murray Brewery limestone of Maastrichtian age. However, Akhtar and Butt 2000 prove Dungan to be of Etruscan age here, whereas in other places it is of Phoenician age. However, irrespective of the age of the Dungan formation, it retains a broken KPG boundary as the Danian is missing. Now this is something from the well. It's a basal part of Karachi 2 well's composite log. Karachi 1 well discovered the Karara shale in 1956, but the well was abandoned. Karachi 2 was drilled nearby in 1959. From Eocene onward, the well drilled a new shale facies throughout instead of the Laki and Dungan limestones and the Pup sandstone, which were the objectives. At 3938 meters, the well penetrated the shale of Maastrichtian age. Another 24 meters was drilled without any change, and the drilling was stopped at 3962 meters. A thin sand influx was observed in the basal Danian shale, which affected the resistivity logs as well. There seems to be a short-lived shallowing of the sea as the Cenozoic began, but without any aerial exposure. This new subsurface stratigraphic find was pursued on the ground by three biostratigraphers, namely Nagappa, 1960, Khurshid, 1972, or Doreen, 1974. The respective biostratigraphic tables are in the proceedings volume. Two field sections were measured in the southern Pub range and one in the Per range where Korara shale crops out. All the three experts could not find a physical evidence to mark the KPG boundary in the field, and samples were collected throughout. The subsequent biostratigraphic studies confirmed the presence of the Maastrichtian and Danian contact falling within the shale, with no facies change across it. This confirmed a continued deposition of a transgressive shale facies across the KPG times. Here, it is classified as an unbroken boundary. It is tried here to arbitrarily map the regions across the Indus Basin where a certain type of KPG boundary could be anticipated. The pink rectangle in this map covers Potwar, Kohat, Hazara regions where the KPG boundary cannot be delineated. The Hangu formation marks an angular unconformity with the underlying older formations, and the Maastrichtian rocks are missing, and so does the KPG boundary. In and around the blue circles, a broken KPG boundary is found with iron incrustations on top of the Maastrichtian rocks, and the Danian rocks are missing. It is a disconformity. In and around the green shapes, an apparently unbroken KPG boundary is found here. The Danian clastics overlie the Maastrichtian rocks marked by iron incrustations, a disconformity again. In and around the yellow circle, based on the well data, the KPG boundary falls within the interbedded chondroclastics and the Maastrichtian basalt in the Badin region. It's a non-conformity. However, the gray oval shows a region where the transgressive phase prevailed across the Maastrichtian Danian times and unbroken deposition continued. No physical evidence of break was found in the field, a likely depot center of the Korara shale. Maastrichtian to Danian transgressive facies of Korara shale represent unbroken KPG boundary within, which is evidenced by a faunal composition of global framework, a rare occurrence. The chart covers the entire Indus Basin. The quality of the slide is regretted. I hope with the projection it might be readable. Due to time constraints, I will just concentrate across the Maastrichtian and Danian quartet. The double-headed red dashed arrow represents the region where the KPG boundary cannot be delineated. Thick black lines mark apparently broken KPG boundary. Same is the case with the Badin region. The difference is that it is a disconformable contact in the formal and non-conformable in the Badin region. Dashed black and white line marks a broken boundary, which is in the Murray Brewery section. The red line on the left represents the status of the KPG boundary in Korara shale based purely on the faunal assemblage as a physical break in deposition, and change of facies is not seen, neither in the well nor in the outcrops. Maastrichtian to Danian transgressive facies of Korara shale represents unbroken KPG boundary within, which is evidenced by a faunal composition of global framework, a rare occurrence. So here are the conclusions. Only the Maastrichtian and Danian stratigraphic contact represents the KPG boundary. It can be an unbroken KPG boundary as in Korara shale, apparently unbroken as between Pup sandstone and Khadro formation, and broken where Danian is absent. Maastrichtian to Danian transgressive facies of Korara shale represent unbroken KPG boundary within, which is evidenced by a faunal composition of global framework, a rare occurrence. Maastrichtian and Darien contact of pup sandstone and Khardro formation respectively is an apparent unbroken KPG boundary due to the presence of iron incrustations on top of the pup sandstone. Maastrichtian and early Eocene contact of Murray-Breuil limestone and Dungan formation respectively represents a broken KPG boundary. Same it is the case with the pup sandstone and Duncan formation contact elsewhere. Late Cretaceous and Danian contact of Gavagar formation and Hangu formation respectively does not represent the KPG boundary as in Hazara region. Late Cretaceous and Phoenician contact of Gavagar formation and Lohart limestone respectively does not represent the KPG boundary as in Samana range. Samini 2000 extends Gavagar formation into Maastrichtian though, but we consider that Gavagar does not extend into the Maastrichtian. And that's why the KPG boundary is not assumed there. Before I close, DGPC is acknowledged for allowing the purchase of the composite log of Karachi to well. Anonymous reviewer is acknowledged for the honorary input to improve the draft. Thanks. Questions are welcome.
Thank you very much for the presentation. All right. Okay, so now the floor is open for the questions. So again, participant who has joined virtually, they can type in their questions. We will enable their mics and then they need to unmute themselves as well, right? So now you can ask the questions. So any questions online? Or
Please.
any questions from here, from the audience? All right.
Full of knowledge and detailed presentation on KPG boundary by Dr. Sahab. My question is how can we use KP boundary in exploration process? Wow.
Okay,
the
so
outcrops, yes, it will help us identifying that the rest of the rocks below that are Cretaceous, and then we can go on making a prognosis of wells according to that. And similarly, while going into the wells, drilling the wells, we may acknowledge, find on the ditch cuttings, we can study that sometimes you do find some residual deposits in the drilling also, and that may indicate that in drilling the well, someone is now about the well is about to cross the Cenozoic and about to enter Mesozoic. Yes, please.
So thank you very much for your presentation, Mr. Nusrat. And now we will be moving forward with the next presentation by Mr. Nawal D. Fraslan, which is on nested discrimination analysis to predict prospective areas.
Thank you very much. So the next paper is from Bicep Friend Lab. The presenter will be Ms. Andy Freslin. She is a geophysicist working as a seismic inversion and reservoir characterization specialist at Bicep Friend, France. She's a part of the rock properties team and is involved in the multidisciplinary studies, both exploration and development in various parts of the world. So Ms. Freslin, the floor is yours. Please continue. Could you please check she is online?
Sorry, you can hear me?
Yes, we can hear you.
Yes.
So,
So
Ms.
you may
Preslin,
start.
you are audible. Could you please
Okay.
continue?
Okay. So good morning, everyone. So my name is Nawal de Freeland. So I am a geophysicist at BC Lab. So today I will present my paper, Nested Discriminant Analysis to Predict Prospective Areas. Okay. So nowadays, seismic inversion is extensively used in cube, so P and S, that can be related to metric properties such as V-shale or porosity through different reservoir characterization workflow. And also, it can be related to facies information, particularly when using approach as a discriminant analysis. So in this paper, in the work that I will show today, I will describe the work performed on the Machuki field onshore Ukraine, and more particularly the seismic reservoir characterization part. And so the objective consists in assigning the reservoir potential of the area in terms of facies distribution. So I will start with the context and the methodologies, and I will show the results and some different points in QC, and I will conclude. Okay, so about the context, on the map here, you can see in red the limit of the basin. So we can see that it's almost entirely in Ukraine. The star here corresponds to the localization of the field. So the work will focus on the Carboniferous reservoir, and more particularly the Tournesian carbonate formation that is located here in the stratigraphic chart. So in the frame of the project, seismic elastic inversion has been performed. So P optimized P and S impedance cube are available. In terms of facies, the system is reduced to three main one: the massive carbonate and the porous carbonate, so and the shale. So in order to be able to have the more reliable prediction, we perform a nested discriminant analysis. So it's a two-pass discriminant analysis, which allow first to isolate the carbonate facies, so both massive and carbonate, massive and porous carbonate. Okay, so now the methodology. So the discriminant analysis is a Bayesian supervised approach, which aims at relating elastic parameters to seismic facies. So first, the work is performed at well using elastic parameters and facies logs for classification in order to select the best a priori model or training sample that will be then used in 3D. So in 3D, elastic cubes coming from the inversion are used in addition to this training sample to obtain cubes of probability of assignment into facies class. So in the case of a nested approach, so this is a two-pass discriminant analysis in order to isolate successively the facies. So this is represented, the methodology of the nested discriminant analysis is shown in the figure. So we can see that we start with the attribute which here are IP and IS with different facies. And so first, in the first part, we will isolate, in our case, two facies, so the shale and the carbonate. And in the second pass, within the carbonate, we will discriminate between the massive and the porous carbonate. And so at the end, we will obtain in 3D as a result of the first pass discriminant analysis, the probability of assignment into shale and carbonate facies and the associated most probable facies cube. And as a result of the second pass discriminant analysis, we will obtain probability and conditional probability of assignment cubes and associated most probable facies cube. Okay, so now I move to the results. So first part discriminant analysis results. So as I said, for the workflow, before pure the 3D analysis, the 3D seismic facies analysis, the discriminant analysis is carried out from well data. So first, at log scale in the depth domain, so to assess the feasibility of the facies discrimination from P impedance and S impedance variables, and then in the second step, at seismic scale in the time domain using the upscale variables. So here the figure shows the data at seismic scale in time domain. So we can see an example of few wells. So we have the shell facies followed by the carbonate one, which is the reservoir in our case. So the first track corresponds to the impedance, the P impedance, the second track to the S impedance, and the third track to the facies. So we can clearly see a major change of elastic response when entering into the carbonate facies, into the reservoir. So this is highlighted as well in through cross plot. So the left cross plot shows the P impedance versus the S impedance colored by the facies. So we can see that clearly there is two different elastic answer for each facies. So the right cross plot shows the results of the first pass discriminant analysis. So we have still P impedance versus S impedance colored by the probability of assignment into the carbonate facies. So the red corresponding to the highest probability. Here the histogram here is the histogram of reassignment. So showing that for the carbonate group here, actually 94% of the sample were already well assigned in the carbonate group before discrimination, before assignment. And this is what we can see here, that before discriminant analysis, the two facies were already well separated. So here, what we can see, so it's that the discrimination of the carbonate facies is clearly driven by the P impedance. And secondly, so the spatial organization after discriminant analysis is consistent with rock physics concept. So with the carbonate with the carbonate facies that have higher P and S impedance values. In a second step, so here we have the results of the second pass discriminant analysis. So here, massive and porous carbonate facies have been defined using a cutoff on the porosity before upscaling. So here we can see a histogram of porosity values distribution. And so with this cutoff that has been defined in order to obtain, to isolate the carbonate that will have the better quality, with the higher porosity. So on the right, we have the P versus S impedance cross plot colored by the two facies, so the porous and the massive carbonate in blue and the porous carbonate in red. So again, so this another discriminant analysis is performed within the carbonate to isolate those two kind of sub facies. And what we can see, it's again we have a quite good discrimination. We have a score of reassignment that are quite high. Here we can see that here we can see the probability of assignment into the porous carbonate facies. So we can see that here the linear boundary between the porous and the massive carbonate is steep. It means that the discrimination in this case is both driven by carbonate samples, as highlighted through those figures. Okay, so now we move to discussion QC. So using those previous the work performed at well as a training sample, the work is then performed in 3D. And so then, in order to handle the uncertainties, so in 3D we obtain a cube of probability, and so in order to handle uncertainties, traces are extracted at well position from the probability cube and compare to the well data. So here the first track corresponds to the initial facies log. The second track corresponds to the upscaled facies log, and the third track corresponds to the probability of assignment into the carbonate class. So here I applied a cutoff at 0.8, and so what we can see, so here in red it's a porous carbonate, but all the column is carbonate. And so we can see that with a cutoff on probability set at 0.8, we have a very good match. Actually, what is predicted as carbonate corresponds well to carbonate at well. So it's expected. It's what we have seen in the previous slide. So we have a very reliable and robust prediction of the carbonate facies. So in order to go further and to explore as much as possible the data, we decided to track the surface. So here you can see a section of the probability of assignment into a carbonate facies. So we can see a quite sharp transition between the shale here with a low probability and the carbonate here with a high probability. So we could track the top limit of the reservoir. For the base, we could do the same. So we can see that there are more uncertainties. The transition is less clear, and actually we can see here at well in the facies log that in the bottom there is a mixed sand and a mixed shale and carbonate facies, so leading to a less sharp transition, but still quite clear. Okay, so and then as a result of the second pass discriminant analysis, so we obtained in 3D two cubes. The probability of assignment actually on the probability of assignment into the carbonate facies. So if we are in the carbonate facies, we will have a higher conditional probability in a way. Okay, so the same work is performed at well. So probability traces are extracted at well position from the cube. So from here, from the probability of assignment into porous facies, and a cutoff has been set. So as previously in the first track, we have the initial facies log. In the second track, the upscale facies. In the third track, the probability of assignment into porous carbonate class with a cutoff set at 0.7. So here also we can see that we could predict the porous carbonate here where it's red, and actually the prediction is quite good as well. We are able to predict the porous carbonate where there is actually this facies at well. Okay, so in order to go further, proportion maps are computed. So porous carbonate proportion maps in the upper part of the reservoir where we have this facies using the probability of assignment and the conditional probability of assignment. So here we have the top actually of the carbonate structure here. And so what we can see when we compare those two maps is quite interesting. So we have the main feature are similar. However, the proportion are lower the proportion values are lower using conditional probability of assignment as input. And it reflects so the lower confidence areas. It reflects where actually the probability of having the carbonate facies during the first pass discriminant analysis was low. And so using those kind of map allow to define areas where we have so higher proportion of porous carbonate, and where it will be more interesting to go for further drilling or for further analysis. Okay, so to conclude, in the frame of the project, 3D elastic inversion has been performed. And so the resulting optimized impedance cube has been used to perform this nested discriminant analysis, allowing to first isolate the carbonate facies. Then, using the result of this first pass discriminant analysis, we could track the reservoir as isolate more likely the carbonate facies. And then, using this nested approach and the second pass discriminant analysis, we could then predict the most interesting part of the carbonate in terms of reservoir properties, so with a higher porosity, and compute map to assess the prospectivity of the area. And so to go further, using those results of inversion, we could estimate other physical property, so such as V-shell, etc. And so using those map of proportion or other output, we could constrain those kind of output are used to constrain geological model building and allow to have more robust model and further reservoir and further dynamic model. So thank you very much for your attention.
All right. So thank you very much for your presentation. So now the floor is open for questions.
Any questions from the floor? Anyone from the online questions? So if there are no questions, we can conclude. And I just wanted to say thank you very much for all the authors and presenters who worked hard and presented their thoughts and technical ideas and share with us. In a very short words, I just like to highlight what 3 papers were all about. The first paper was presented by Abid Riaz about the improving depthing uncertainties. It was about the full wave inversion in seismic data processing will help determining geological subsurface imaging, which will improve our ability to drill at right location, and that will be a futuristic approach in seismic processing. The key support will be available for better and more accurate velocity model. That's the building block of precision and depth processing. That was the first paper. The second paper was presented by Mr. Nusrat Kamal online, and that was about the Cretaceous and Paleogene boundary in Pakistan stratigraphy. So he has highlighted the importance of the Carrara shell, which is identified the ideal KPG boundary sedimentary sequence on the global scale. And he compiled the data about the Cretaceous and Paleogene boundary throughout the Pakistan, and that's what he has presented in his paper, and highlighted the nature of contacts at various locations and devised the new nomenclature, which I thought it's a new nomenclature, broken, apparent, broken, and unbroken. And he also especially highlighted the importance of the Carrara Shale and Murray-Bravely limestone, which uses, particularly he highlighted about the importance and the contact of the K and PG boundary. The third paper was an overseas paper, a nested discriminant analysis to predict prospective area. The objective consists in providing key elements to assess the reservoir potential of the area in terms of facies and helping to predict interwell reservoir facies distribution through a model-based elastic inversion and seismic characterization workflow. That's something which all the explorationists who've been involved really wanted to resolve such kind of problems. By saying this, I thank again all of you. And if you'd like to add something.
No, thank you very much. I think you have covered most of the things which we have just gone through in the last three papers. So thank you very much, audience, for your listening time. And thank you very much, presenters, for presenting such a wonderful papers. Thank you.
So now we would like to invite Mr. Tariq Hasni